Good morning all of you. In this video I am going to discuss the potential for a spherical shell, uniformly charged spherical shell. Okay, so like this, if suppose this is our spherical shell, the charges are distributed uniformly like this. So the charges are distributed like this. If it to find the potential for this spherical shell inside and outside, first we choose a area element, small area element. This area element will be uniform. So it is if you take another area element of like this, the charges present in this area element is also same here. So like that we have to choose one area element. The charges are distributed uniformly. So right. So next let us take a small distance. The distance of this area element is r, radius of the sphere, because this is here I am going to discuss the spherical shell. Spherical shell means we can see the example tennis ball. Let us take a tennis ball as an example for spherical shell. So inside the spherical shell there is a empty and the charges are distributed over on the surface only. Okay, for this type of spherical shell I am going to discuss the potential. Our area element is on the surface, and the surface will be at the distance r from the center. So I am going to take that as a radius of the sphere. So now let us choose a point P. So like this, the point P here, the point P is at a distance z from the origin, from the center of the sphere. Okay, here I am going to calculate the potential. The distance from this area element is r. Okay, so we know that the general formula for a potential is V is equal to epsilon naught integration. So 1 by 4 pi epsilon naught sigma divided by r into the area element dA dash. Okay, so here sigma means charge density. Next, so for this I need this 1 by r value. So using this 1 by r value, if you substitute this 1 by r value, and if you take the area element dA dash, we can easily calculate, you can easily integrate this potential. So V is equal to 1 by 4 pi epsilon naught. So first we need 1 by r, right? So using cosine rule, we know that r square is equal to r square plus z square minus 2rz cos theta dash. If this is cos theta dash, see the position, the vector will be like this. So by using parallelogram of vector addition, we can easily get this equation. So this is the distance z, vector z, this is the position r, so radius r, and this is r. The distance area, the r means the distance from this area element and the position where we are calculating the potential. And this is this position, this area element is from the origin, so which represents the radius vector r. So using this rule, this vector diagram, we can easily get this equation. Okay, next, so for us we need only 1 by r, right? So next, so then r is equal to square root of r square plus z square minus 2rz cos theta dash, and 1 by r is equal to 1 divided by square root of r square plus z square minus 2rz cos theta dash. Okay, so now let us substitute here in this equation number 1. Next, so therefore V is equal to 1 by 4 pi epsilon naught integration sigma divided by r means, so root of r square plus z square minus 2rz cos theta dash into dA dash. So here for this problem I am going to take spherical polar coordinates. I am going to express this equation in spherical polar coordinates, because if you take in spherical polar coordinates, it's very easy for us to simplify. Okay, so instead of taking Cartesian coordinate, I am going to take spherical polar coordinates. In this spherical polar coordinates, for area element dA dash, we know that r square sin theta dash d theta dash and d phi. So this is the area element. So let us take here and substitute v is equal to 1 by 4 pi epsilon naught integration theta varies from 0 to pi and 0 to 2 pi varies from 0 to 2 pi, and sigma is a constant, take that outside, into dA dash means, so and substitute here r square plus z square minus 2rz cos theta dash into d theta dash and d phi dash. And if we integrate, we know that, let's see, so integration of d phi means phi always varies from 0 to 2 pi, and you will get 2 pi. So for this part I am going to write directly 2 pi and take the 2 pi outside. So v is equal to 2 pi sigma divided by 4 pi epsilon naught integration 0 to pi d theta dash divided by square root of, sorry, here I forgot to write sin theta dash. Okay, so sin theta dash into d theta dash divided by square root of r square minus z square, sorry, plus r square plus z square minus 2rz cos theta dash. So this is in the form of, see, integration of root of f of x into f dash of x dx. For this we will get root of f of x. So if we want to write in this form, see, differentiation of cos theta dash minus sin theta dash, but here already minus is there, so minus into minus plus, so plus will be there, no problem, but the coefficient 2rz is missing here. So that's why I am going to multiply and divide it by 2rz in this equation. So 2rz multiply and divided by 2rz. Next, now this is, so this expression is in the form of f dash of x into f of x. So if we differentiate this one, this is constant 0, this will be constant 0. So then we will get minus 2rz into cos theta sin theta dash. Differentiation of cos theta dash sin theta dash minus as it is writes. So cos theta minus sin theta into coefficient 2rz. So sin theta dash 2rz will be the f dash of x. So here it is there. So now we have to write in this form root of x. So is equal to pi gets cancelled and write it is, and 2 gets cancelled, right, and the remaining is sigma divided by 4 epsilon naught rz into root of f of x. F of x means this one, r square plus z square minus 2rz cos theta dash, limits varies from 0 to pi. Understand? So this is our f of x, v potential. So now we are going to simplify this one by applying upper limit and lower limit. V is equal to sigma divided by 4 pi epsilon naught z. So applying upper limit and lower limit, so then we will get root of r square plus z square minus 2rz cos theta means cos pi means minus 1, minus into minus plus, minus lower limit root of r square plus z square, cos 0 means 1, so minus 2rz, which is equal to sigma divided by 4 pi epsilon naught z into see a plus b whole square formula. So it is in the form of a plus b whole square. So just write this r square plus z square minus, so sir, this is r plus z whole square and this is r minus z whole square, a minus b whole square. Okay, so this is the general expression. So now let us take a condition. If suppose if you want to calculate the potential inside and outside, see for outside means outside this pair. So V is equal to sigma divided by 4 pi epsilon naught z into, see for outside z is greater than r, z is greater than r. So this here, so instead of taking r minus z, I am going to take z minus r, because inside the root we have to get the positive value. Okay, so z is greater than r. No, so now I am going to take, instead of taking r minus z, I am going to take z minus r. Okay, so r plus c, and the square root and root cancel, square and the root, so remaining is r plus z minus, and instead of taking r minus z, I am going to take z minus r here. So z minus r, so is equal to V is equal to sigma divided by 4 pi epsilon naught z r plus z minus into minus plus r. So z and minus z cancel, the remaining is V is equal to sigma r plus r 2r divided by 4 pi epsilon naught z. I think that pi get cancelled, right? Once again, so sorry, here the pi is already I cancelled there, so here pi will not come. So answer is 2 sigma r divided by 4 epsilon naught z. Okay, 2 sigma r divided by 4 epsilon naught z. So this is the potential of a spherical shell, uniformly charge distributed spherical shell outside. This is electrostatic potential for a spherical shell outside the spherical shell, and the potential is varies as inversely. If the distance move further from the spherical shell, it will decrease as 1 by r. R means distance, or you can take that as 1 by z, something like that. Next condition. So now the potential find for inside the spherical shell. Now I am going to calculate the potential inside the spherical shell. The charges are distributed outside, but now I am going to calculate the potential inside. But we know that if the charges are distributed outside, the electrostatic potential, the electrostatic energy, okay, or electrostatic field is 0 inside the hollow spherical shell. But let's see the potential. So inside, okay, here I am going to take for inside r is, see this r radius is greater than z, because if this is our spherical shell, this is the radius r of the cell, I am going to choose the point here inside the potential distance z. So here r is greater than z. So when r is greater than z, so this equation does not create any problem. So write it as it is. So sigma divided by 4 pi epsilon into r plus z minus r minus z. Next, and r plus z minus into minus, minus into plus minus, minus into minus plus. So r minus z, right? Okay, minus r plus Okay, so r plus z. So next, so plus r and minus r get cancelled, remaining is 2z. So write here v is equal to sigma divided by so in the previous problem I did not cancel 2, that numerator 2 and denominator 4. So see, sigma r z 2z divided by 4 epsilon naught z, and 2 and 4 get cancelled. V is equal to sigma z divided by 2 epsilon naught so V is equal to sigma divided by 2 epsilon naught. So this is the potential inside the hollow spherical shell. So the potential is constant, but electrostatic field is 0. Okay. Next,